Yeah, thanks a lot for having me here. It's been really fun. I've learned many things. My first time in Zurich. So yeah, I'm gonna tell you about some recent work that we put out with Julio Parra-Martinez on naturalness of static love numbers for black holes, and also some non-renormalization aspects of them associated with neutron stars and other compact objects as well. But yeah, so I apologize if there is some overlap with what I'm gonna say and what has been said, for instance, by Filippo or Lam yesterday. But just to give some background and make sure that everyone is on the same page, let me give some motivation. So love numbers are these coefficients that measure the deformability of a object, of a body under some external tidal fields. And they are the gravitational analog of polarizability, so I'm sure everyone is familiar with that concept. So the simplest case where one can introduce this is the case of Newtonian gravity. And in that case, the gravitational potential solves Laplace's equation outside the body. And one can consider adding some external source. And I will, in this talk, I will mostly talk about static deformabilities or static external sources. And this source will have different multiples. And then one can, as we have seen in great detail, for instance, in the talk by Filippo, one can solve, match this external field with the boundary conditions at the body and find that this body deforms because of the external tidal field. And this deformation is captured by some coefficients which parameterize the, if you want, multipolar response of the object. And these are called the love numbers. So, of course, the natural expectation for the value of these numbers is for them to be over the 1. And as we've seen, this is what happens in cases where they're non-vanishing. However, it has been known for some time that love numbers, static love numbers, are actually vanishing for black holes in 4 dimensions. But there is a very surprising and maybe interesting pattern of how this happens. And so let me review this. So love numbers are known to be non-vanishing if the black hole is probed by time-dependent perturbations. And we have just seen explicitly that this is the case in Luca's talk. Yet they vanish when you consider static external fields, but only in 4 dimensions. And this has been known for linear perturbations for some time, and in the last 1 or 2 years, there have been also many very interesting developments for nonlinear responses by some people in this room, and as well as other people. So another interesting aspect is that, as we have also seen this morning, the vanishing of love numbers is not valid for neutron stars. So they're, in general, static love numbers are non-vanishing for compact objects, including neutron stars. So this pattern is quite puzzling. And if you want, from particle physics, in particle physics jargon, you might say that it seems to violate naturalness. Okay, so this problem becomes sharp in the worldline EFT formulation. So this will be the formulation I will adopt. And please interrupt me for questions at any time. So the question we wanted to address was why does this happen? And there has been a considerable amount of great work that has been done in the last few years to address this puzzle, mainly in the context of black hole perturbation theory. So when studying the equations for the perturbations of black holes. So for linear perturbations, there have been some nice proposals, and we have seen a talk by Lam where he has reviewed ladder symmetries. There is another symmetry that also can explain vanishing of static love numbers by Sergei Dubovsky, Misha Ivanov, and Haralambos. And this work, these originally were developed for linear perturbations. More recently, there have been very, very interesting works in which this was, in fact, extended to a class of nonlinear responses, in particular those that can be excited by axisymmetric perturbations. Yet, this left open some questions. In particular, it was not clear if this pattern is valid at full nonlinear order. So for electric tides that are not probed by axisymmetric perturbations, and for magnetic tides which vanish always for axisymmetric perturbations. Moreover, from the point of view of the worldline EFT, it was not clear why there was no running for some of these Wilson coefficients, if you want. And also, these symmetries were not, well, the action of these symmetries in the worldline formulas was not clear. So there have been some recent developments which make the linear ladder symmetries, which make explicit the action of the linear ladder symmetries in the worldline, but it was not clear in general how to do this at nonlinear order. So before explaining our proposal, let me briefly remind you what the formuling we're using does. So given a compact object, we can look at it from far away and describe it as a point particle moving on a worldline. And I have tau is the affine parameter that parameterizes this worldline. And for a minimally coupled particle, I just have the massive point particle action that I write like this. And moreover, this worldline is coupled to pure gravity in the bulk. So there is a bulk action which describes gravity in 4 dimensions. And this, I will take it to be just the Einstein-Hilbert term. OK, so this is the starting point. But as we have heard, black holes in general might have some, compact objects in general might have some finite sized terms. So they might not be simply minimally coupled point particles, but they can have multiples or other finite size terms. So in order to describe those, the way in which usually one approaches this problem is one looks at terms that depend on curvature. But since we are, so all of my talk will be about non-spinning black holes, so Schwarzschild in 4 dimensions or Schwarzschild-Tangerlini in higher dimensions. Since we are in a Ricci flat background, then the non-minimal couplings are all defined in terms of the Weyl tensor, because the Ricci tensor and the Ricci scalar, they can be redefined away by field redefinitions. So we look at the Weyl tensor, and then this can be decomposed in terms of electric and magnetic components. So C is just the Weyl tensor, and C dual is just the dual tensor built out of the Levi-Civita tensor. So these are the 2 building blocks. And for most of the talks, I will, well, for the rest of the talk, I will always work in the rest frame, in which the black hole is at rest. So in this frame, we can build higher multiples out of these two index objects just by taking derivatives, spatial derivatives, and then taking the symmetric traceless combinations. So this will be just the spatial parts which describe the static response. And then in addition, one can take time derivatives. But let me postpone that to the next slide. So the first finite size terms that you can write are intrinsic multiples. So you could write a quadrupole of electric type. You could write also magnetic type multiples. But most of these talks, I will neglect these because these are absent for black holes. If you want, these are a consequence of the O'Hare theorem. And so we will set those to 0. But then one can go to higher orders and consider tidal effects. So the leading order terms are what are known as associated to linear log numbers. And this corresponds to operators that are quadratic in the electric or magnetic tensor. So here I'm not writing mixed terms at linear order because they vanish by parity. So these describe the static response. There are no time derivatives. And then one can go to higher orders and define the nonlinear deformability, which is associated to higher powers of E, B, or mixed terms. Then, in addition to the static response, one can consider also the dynamic response, in which one writes operators that include time derivative. And at first order, or in general odd orders in frequency or time derivative, these are a dissipative, these describe a dissipative response, as we have seen also in Luca's talk. And in general, to describe dissipative response, one needs to use the in formalism. So I will not go into details about that, but that's a standard tool. More general, you can have also dynamic love numbers, which are conservative, and they have even powers of frequencies. Okay. And so this is the full set of finite size terms that you have to worry about. So now, how do people usually, compute those love numbers? Well, as we've seen, one usually performs a matching computation between the UV theory, which is if you want four-dimensional GR, and the worldline EFT. And in the full theory, one solves an equation for the perturbations. And then this is matched to the contact terms coming from the love number operator in the EFT. So in addition to this, of course, one should worry about non-linearities in the EFTs, And these, in general, from an EFT point of view, they can induce mixing and running of the operators. So this was studied in detail in the case of probe scalars, where it was shown that individual diagrams that are associated to non-linearities in the EFT are non-vanishing, but then they sum up to 0. And until now, until recently, as mentioned in the previous talk, there was no explicit computations of these, if you want, nonlinear effects in the EFT, but there has been great progress. But basically, what we want to understand is why do these nonlinear diagrams, these higher order diagrams, not contribute to running? What protects them? Okay, so let me start by summarizing what our proposal is, and then try to explain you how we arrive at this. So the structure that we find is that of an accidental symmetry that is there only in the what we call the static sector, but more correctly, probably one could call it the stationary sector, by which I mean all time-independent matrix perturbations of the Schwarzschild background. And this is a symmetry that is there at the classical level. And some of its aspects are unique to 4 dimensions, and that explains why love numbers can be non-vanishing in higher dimensions. So this symmetry is there in the pure gravity, if you want, Einstein-Hilbert action, but is broken by some solutions, or if you want, by the worldline couplings to a massive point particle. So there is a break in there, but this breaking can be, if you want, the symmetry can be restored by assigning selection rules, particular to the mass of the object. And the selection rules that come from this, by assigning a spurionic transformation rule to the mass of the object, and the selection rules that derive from this symmetry allow us to argue for some consequences. In particular, we can argue for this symmetry implies the radiative stability of love numbers, so there is no running in the EFT. And this means that if you set the Wilson coefficients to 0, those stay 0 at every scale. And moreover, all the analytic contributions associated to the perturbative expansion are controlled by the spurion analysis. And this will imply in particular the vanishing of love numbers for black holes in 4 dimensions. And let me stress that another interesting aspect of this is that this is completely symmetric between magnetic and electric responses. So, and it's valid the full nonlinear order. Okay, so the way we derive this is by starting by studying, since we are interested in time-independent perturbations, it's natural to work with a Kaluza-Klein-like reduction in which we reduce with respect to the time direction, but we're not compactifying time. So time is kept infinite, but we use, if you want, a field variable which is compatible with this reduction. So this phi, if you want, you can think of it as a dilaton. It's like a dilaton. This AI is a three-dimensional vector, which you can think of it as a graviphoton. And then here, the spatial metric, we are redefining it by pulling out a factor of the dilaton in such a way that the kinetic term of this phi field is simplified. So we can rewrite the Einstein-Hilbert terms in terms of these fields. And what we get is this action. So let me stress now that this Ricci term is just the one associated to the three-dimensional metric gamma. And then I have this scalar field and this vector field. So this looks maybe nice, but is not yet enough. So here I'm neglecting, of course, time derivatives. One can include those, but they're not. Then the action doesn't take a particularly nice form in terms of these fields. So the next step is, since we are working in this time with this time-independent field, and since this vector now is a three-dimensional vector that only depends on spatial coordinates, we can dualize this vector to a pseudoscalar. So one needs to do it carefully because there are some dilaton factors in this. But in this, one can derive this exactly. But essentially, this is the end result. So the vector associated to this field strength is dualized in this way. And then the kinetic term that I wrote, which had scalar and the vector components, now takes this form in terms of the dilaton and the axion, if you want, the pseudoscalar. So this looks much nicer because if you introduce a complex scalar in some way that might be familiar to some of you who worked in, I don't know, supergravity or string theory, one can introduce this complex scalar and see that the action that we wrote before takes this very nice form. So in particular, there is the Einstein-Hilbert term and then an additional term, which one can recognize as the nonlinear sigma model for SL2R broken to SO2. Okay, so this exhibits that in the static sector of GR, in the time-independent sector of GR, there is this accidental symmetry. And this is not entirely new. The derivation maybe is different from what it was historically done, but this was noticed already last century, 50 years ago, in the general relativity community, in particular at the level of the equations of motions, where this symmetry was known as a solution-generating symmetry. So that means that given a solution, a static solution of GR, one can build a new solution, can derive a new solution by applying an SL2R transformation. Okay, so let me show you how this symmetry acts. The action is the obvious one. So you have a fractional linear transformation, and you have this, of course, relation between the parameters. And well, there are two kind of special elements in this group that generate the whole group, and those are sometimes called S and T transformation. So S is this transformation that sends Z in -1/Z. And if you want to, you can think of this as a Z2 symmetry inside this SL2R. So now this might seem trivial, but in terms of the original field variables, it's a very nonlinear and complicated transformation. So in addition, there is also parity, which if you want to sense the axion to minus itself, and you can express it in terms of complex conjugation. Okay, so this is the symmetry structure at the level of pure gravity. Now we can, it is actually convenient, sorry, maybe I didn't say it, but this complex scalar was defined in the upper half plane because this field phi is real. So now this is, if you want, the Poincare half plane model of hyperbolic geometry, but now you can map it to the unit disk, to the disk model by using a conformal map. And we call this new complex scalar variable W. And after you do this, the S transformation takes this very simple form, which is just a Z2 symmetry which sends W in minus W. So now the action takes this different form, but of course nothing has changed in the physics. So what I think the new way of thinking that we have about this symmetry, which was already known, as I was saying, is just that it is an accidental symmetry of this time-independent sector of GR, and that actually it can be promoted the spurionic symmetry even when it's broken by a solution. So let me discuss a bit about this. So in the Minkowski vacuum, the Minkowski vacuum corresponds just to Z equal I of W equals 0, and this shows that, if you want, this explains why the nonlinear sigma model was SL2 model SO2, because this SO2 was linearly realized. But now when we look at the Schwarzschild background, and the relevant coordinates are isotropic coordinates, these are the coordinates, if you want, that are compatible with the field basis that I've chosen. One finds that, well, the Schwarzschild metric takes this form, where X is just this combination, capital X is just this combination. And one can match this metric to some background values for the field variables I decided to use. So now one can see that if I look, for instance, at the S symmetry, more generally you can do with SL2R, but let me just focus on S from now on. This symmetry is broken by this solution unless I assign some transformation law to the mass. So once I assign this law, then the symmetry is restored, and I have a background which is symmetric under this spurionic rule. So this is in complete analogy, if you want, for those of you who are familiar with the chiral Lagrangian in QCD, this is the same as assigning spurionic transformation rules to the quark mass matrix. Okay, so this is what we can do at the level of the background. One can understand this also at the level of the worldline. So in the worldline, one can first of all realize that the only term that is relevant for the classical response computation is the linear coupling. And then you can rewrite this in terms of W, and then we can see that the same spurionic transformation rule emerges. And let me also say that in order to do the matching, instead of using EMB, we will use W and gamma. And one can rewrite EMB in terms of W and gamma, and the linear order. These are the first two terms in this expression. Okay. Okay. So now having determined how this if you want, how the symmetry is realized on these variables, we can, as I was saying, we can phrase our matching computation in terms of W, or our response computation in terms of W, and we can imagine putting a source which is now defined in terms of W and looking at the tail generated by the response of the body. And this will take a form of an expansion in X, where X is the combination I said before. And in 4 dimensions, so this expansion has always integer powers of X. In particular, one can check that the contact term, if you want, the love number operator corresponds to this power of X. Now we can try to use the symmetry to constrain these terms. So we see that if we apply this S transformation, W goes to minus W, and then M goes to minus M. And so if this symmetry is a valid symmetry, then this term cannot be generated. Okay. If we do this at the level of the worldline EFT, where this is always, well, these constraints, if you want, the running, we can use this argument to argue that love numbers are not renormalized, and this is a statement that is valid to all orders in the worldline EFT, which is always, if you want, a series expansion, a Taylor expansion, a perturbative expansion in G. So this explains, if you want, the naturalness of love numbers, because it tells you that if you start with something which is symmetric, then you can never generate these terms that break the symmetry. On the other hand, if you imagine doing a full response computation, you can argue that, as I was saying, in 4 dimensions, the full response is an analytic series in X, because it corresponds, if you want, to integer. So love numbers corresponds to integer powers of X. And this is a property that is special to 4 dimensions, as I will show you in a second. And so the vanishing part of the statement is only valid if you want, there are no non-perturbative contributions in X. Is this clear, or is there any question? Yes. Yeah, so I already, that's the minus sign that you're talking about. It's here. Yeah. That's why K is forced to be 0. Yeah. And so yeah, let me stress that what we are saying here is also something well known in energy physics. Is the same thing that happens, for instance, in non-renormalization theorems in supersymmetric gauge theories, where one can use Spurian analysis to constrain the perturbatively generated part of the superpotential, but then one can have non-perturbative components that are not constrained by the selection rules. Okay. So now what I showed you here was at linear order. One can try to generalize this at nonlinear order. So one can look at the nonlinear response. And now here you can have several different contractions with different indices for all these operators, but you can always choose the sources in such a way that you select, if you want, one of these, you probe one of these operators, and then you can perform the matching by looking both at W but also at gamma, and these will have different transformation rules. And these are both needed because, as I was saying, the expansion, if you want, of these operators contains both W and gamma. Sorry. Yeah, that's the point. So, in some cases, these coefficients are forced to be 0 because gamma does not transform. Depends on the value of this n. Yeah. So n is, if you want, is some integer that parameterizes the order of non-linearity. So n equal 1 for me is the linear response because it corresponds to a quadratic operator. N equal 2 is a quadratic response, and so on. Yeah. It's just that I think that from the point of view of the worldline, you just have a diagrammatic expansion, and some of the equations of motions that you call so here there is no time dependence. I'm just in the static sector. So yeah, but I think that maybe you can separate the arguments in if you want a statement on W plus the use of constraints. Yeah, maybe we can talk offline, but I think it's just a way. I think the worldline is just a diagrammatic way to solve Einstein's equations. So some of these equations will be constraints, some will be associated to equations that were not constraints. Okay, so we can do this for nonlinear for general n, and then we can put sources only for W, but then match both, if you want, W and gamma. And the transformation rule here under this Z2 will be different depending on the value of n. And in the case of n odd, one can see that the response of W forces this case to be 0. In this case, depend linearly on the lambdas, and so they are forced to be 0. In the case of n even, one looks at lambda, and the opposite is true. So this shows that static love numbers are not renormalized to all orders in the worldline EFT. And as I was arguing, in the case of d equal 4, the response is analytic in X, and so in addition to being non-renormalized, they are also vanishing. Okay, so now let me remark on some aspects of the symmetries, on some predictions that we can also make beyond the case of static love numbers for black holes. So the first remark is that, I'm looking at the symmetry that is an accidental symmetry, so it's there only for these time-independent perturbations. So as soon as I look at time-dependent terms, this symmetry will be broken. But the first terms where this happens are terms with an even number of derivatives in GR. And so this has two consequences. So the first consequence is that dynamic love numbers and also dissipative dissipation numbers, if you want, can be non-zero. But the leading dissipative tides, they are not renormalized because they cannot get contributions from terms with two derivatives. And this is consistent, for instance, with what we have seen in the previous talk, where Luca had shown us some, if you want, dynamical responses, and the term which was linear in omega didn't have any logarithm, differently from the terms of higher order in omega. So this, if you want, is an explanation, one possible explanation of why that is the case. And we expect the same to hold also at non-linear order, but at first order in derivatives. Then another comment is that the argument we have at the level of the worldline does not depend on whether the object is a black hole or some more complicated object. So the non-renormalization part of the statement, as far as the leading point particle coupling, so if there are no if one neglects quadrupoles or higher multiples for the neutron star, as for instance Filippo was showing us in the case of spherically symmetric neutron stars, then one does not expect any running by the same argument as I showed. And therefore, one can argue for the absence of logarithms, which is also consistent with what has been found. Okay. Another comment is that, again, since this is an accidental symmetry, this will be in general violated as soon as you extend GR, either by the addition of higher curvature terms. For instance, if you write a Riemann cube term, this term violates the symmetry, and it has been also shown by explicit computation that in general love numbers are non-vanishing in this case. The same is true also if you add the cosmological constant, or if you couple two generic matter fields. For instance, there was some recent work regarding coupling to fermions. And more generally, since the symmetry I showed you was only valid in the time-independent sector, if you allow if you allow virtual particles to be time-dependent, as would be the case in quantum loops, then the symmetry generically will be broken. So we expect, if you want, love numbers to be vanishing only in the classical limits. Yes.
So there is no reason why the diagram of the symmetry broken.
Well, yeah, so the symmetry is broken, but the claim is that all the loops that come from the point particle insertion, those do not renormalize. Yeah, of course. Yeah, yes. So that's why I'm saying only the universal nonlinearities from the leading point particle coupling. So if you want the mass, the GM coupling, those will not induce loops. Yeah. Yeah, no, I agree. There can be non-linearities associated to multiple insertion of the love number operators, and those might induce a running. But if you, so for instance, the computation we saw this morning for neutron stars was not including those, right? Like the running that was absent was the running from the leading point particle coupling, where you just have the massive point particle. So those, I think it's a non-trivial prediction that even if you take a neutron star, there are no logs associated to those couplings. Okay, so how am I doing with time? Okay, so yeah, I'm almost done. Just one more slide. Then, if you're interested, I can tell you more. But as I mentioned at the beginning, there was part of the mystery of love numbers is also that they are vanishing only in 4 dimensions. And from this way of looking at things, I think the way we have to understand this is that 4 dimensions are kind of special. First of all, because the step in which we dualize the vector to a scalar was only valid in 4 dimensions. And so this tells you that in higher dimensions, magnetic, if you want, and electric or tensor tides, they are different. And this is also explicit in explicit matching computations. And moreover, another difference comes from the fact that the expansion parameter, if on the perturbative expansion parameter that I called X in my previous slide, in the case of higher dimensional spherically symmetric black holes, as this form. So there is a non-integer, well, there is a non-trivial power of R. And so the love number of operators that are associated to some fixed power in 1 over R, in general, can correspond to some fractional power of GM. And so in this sense, these love numbers that are associated to fractional powers of GM, they are essentially non-perturbative contributions from the point of view of the worldline EFT. Because of this, because of the fact that the series expansion, in particular the love number operators in higher dimensions, they are, if you want, non-perturbative, non-analytic contributions, they are not restricted by our selection rule argument. But we can, on the other hand, we can say something about those love numbers that are associated to an angular momentum, such that this combination L hat is either integer or some odd half integer, if you want, some odd multiple of 1/2. So in the first case, an argument similar to the one I showed you before applies, to the one I showed you before in 4 dimension applies, and then we can argue for both vanishing and non-renormalization. In the case in which we have an half integer, we can see that there are diagrams that can mix at the same perturbative order, and they're allowed by the symmetry. And this is consistent with the fact that these love numbers are known to have a running, so they have logs appearing in the explicit computation. On the other hand, when we have this combination that is not integer, then we can use our EFT to argue for non-renormalization, but we don't have control on the non-perturbative matching contributions. And so those love numbers are non-vanishing, but they do not run. But here, as I was saying, notice that since we couldn't dualize the vector to a scalar, now I'm using a restricted symmetry in which I only transform the dilaton and I don't transform the vectors. And this is enough to constrain the scalar, if you want to respond, scalar love numbers or the tensor type love numbers. In addition, we can also use a similar argument to understand some aspects, if you want, of tidal response of shift symmetric scalar fields coupled to gravity in a Schwarzschild background. And this can also unify some of these tidal love number statements with the well-known no-hair theorem, and can also explain why operators that are shift symmetric but break, if you want, some Z2 symmetry associated to the scalar, such as quintic Galileans or if you want, scalar Gauss-Bonnet operators, they can allow for a hair. So this is, I think, a nice way to unify, to look in a unified way to these different aspects. So, and let me comment also that, of course, the vanishing here for the response in the case of scalar fields is only valid for some class of tides, those with that I'm calling here even tides. So I'm happy to tell you more if you're interested, but I have a backup slides if you're interested in this. But what we have is fully consistent also with the explicit results, for instance, by Justin and collaborators, that some other tides are non-vanishing in the case of odd, if you want, tides. So yeah, let me stop and conclude here. Take your questions. So we presented some, I think, new way of thinking about selection rules for love numbers, which is based on an accidental symmetry, and that can be applied for static response of black holes, but also for some interesting extensions. So in particular, I can explain also non-renormalization for neutron stars and for the leading dissipative tides. And this is consistent also with known results for non-vanishing love numbers in higher dimensions and in extensions of GR. So we have already some preliminary results published that extend the symmetry to the case of Einstein-Maxwell. So if you want electromagnetically charged black holes, and we also understand how to include NAT charge. So if you want tau NAT black holes, and the extension to spinning black hole is work in progress, but we hope to report on this in some near future. So thanks for your attention.
Thank you for the nice talk. Question.
Thanks for the talk. I don't have a question, I have a comment. So this SL2 symmetry, it's called the Eller symmetry.
Yeah, I'm citing, it was cited here, yeah.
Right. Very good.
Cited here.
Very good, okay. And it's actually the symmetry that generates electrovacuum solutions from vacuum solutions, has been used many, many times.
Yeah.
And also use it with a paper I wrote with Tony, where we show that this symmetry is beyond the vanishing of the null numbers to orders. And also, if you want to go to spinning black holes, as you just mentioned, you can use the zero group, which is when you have two abelian symmetries, not only the time shift, but also some rotational symmetry. Then you can reduce your four-dimensional theory to 2 dimensions. And things start becoming more interesting because there the corresponding Euler group becomes zero group, which is infinite dimensional, and actually it's an infinite dimensional affine Kac-Moody algebra.
Yeah.
Which is also beyond the vanishing of the love number of the Kerr solution. So
yeah, so I'm happy to chat after. So my understanding was that those observations were applying to axisymmetric perturbations were reduced to lower to 2 dimensions by using axisymmetry. So I was aware of this, and I think it's a very nice step. I think the thing we are doing beyond that is that we are not restricting ourselves to axisymmetry, and we are also using this extra spurionic transformation rule for the mass that tells you something more beyond that. But thanks, yeah.
Thanks very much for the nice talk. I was curious, have you thought about 3 dimensions, BTZ black holes?
Yeah, good question. No, not really. I didn't look into that.
Because there, yeah, we found that the love numbers are non-zero and proportional to cosmological constant.
Okay, yeah, I haven't tried. So a general comment is that the symmetry I described is broken by the cosmological constant term, even in 4 dimensions. So I think it's not surprising that probably also in 3 dimensions, the symmetry will not be there if you have the cosmological constant. And BTZ black holes require a cosmological constant to exist. But I haven't looked in details, so yeah, thanks for the question.
More questions? So, sorry, maybe yeah. I asked something myself. Yeah. Here, in more than 4 dimensions, you only have this transformation of the scalar part, the dileton part, right?
Yeah, so yeah, we don't have anything to say about magnetic
You don't have
response.
anything to say about the.
No, we didn't. I mean, I think one can try to do something, but in this, yeah, for now we only looked at the, if you want, parity even sector. Yeah, I don't know if. Yeah.
That's true, but it's surprising because the pattern whether the number is vanish or at the value is more complicated.
Yeah.
It's not just L integer or C integer, but it's a combination of E.
Mhm.
But isn't it the same combination? But no, it's not.
Yeah, exactly.
Okay.
Yeah, so here I was restricting only to electric and tensor type. Yeah.
Yeah, it breaks down because you cannot dualize. the
Yeah.
picture.
Yeah, that's what I was trying to say here.
More questions? If not, let's thank Alessandro.